All right, hello, welcome. So this is the video about the FRDM-AUTO board for automation. So this is a nice little shield that will enable you to kind of start dabbling in electrical control systems and also be able to connect it up to the internet. So um, the purpose of this video is to kind of go over the page a little bit and kind of go through the schematics so you can get just a quick overview of what is all on the FRDM-AUTO. So if you got to this video, that means you at least made it to the page for the Monkey Do project and the FRDM-AUTO board. So you got a chance to read through it, and you saw that some of the main features are, we have a high current solid state relay, a low current solid state relay. There's some convenient terminals for connecting ring fork terminals or lugs. There is a pair of optocouple inputs for doing optically isolated inputs, very common in industrial networking. A temperature sensor, onboard temperature sensor. There is sockets for this RNXV serial to Wi-Fi interface. Now that's interesting because you can get Wi-Fi to serial, but the footprint's also compatible with the XB series of communications modules for doing Zigbee. So there's a bunch of stuff. There's even a Bluetooth module as well. There's an optional RS-45 interface, so it has an RS-45 transceiver for doing RS-45 networking, which is another common industrial networking interface, and an optional MAX 31855. It is a thermocouple to digital converter. It kind of does all the heavy lifting of interfacing a thermocouple, so you can solder that on the board. And there's pads for an Omega, a standard thermocouple interface. So that's kind of cool. Now the picture here is a version that I built. Has everything except this thermocouple interface. Now this board, you'll be able to use it with pretty much any of the FRDM boards. Now I used it in the Monkey Do project with the K64F, and I used the wired network that was on the K64F, and not the wireless. But you certainly get a nice, easy way to add wireless. Now, as far as the files that are provided here, there's a couple different packages. The first one is if you just want to order the boards to make them yourself. I have this. I'm sorry. There are down here is the Oshpark Gerbers. So what Oshpark is just a low cost board house. They're not actually a board house. They just amalgamate orders and go to a board house to get them done cheaper. And it's very common now in the open hardware community because it's fairly low cost. So the only thing special about these Gerbers is that uh, the naming conventions are correct for Oshpark to do direct upload. Now, there are some schematics. I just gave a PDF directly on the web page, some assembly prints, but all of this stuff is in the complete design package. So let's take a look to see what's in the complete design package. Now, I already have it unzipped to this folder here. Now, in the root directory are the raw design files. So if you have access to Altium Designer, that is what all of the circuit boards were done in. If not, you have everything you need to build the design and kind of hack at it. And that's under build package. Now under build package, I have a couple other folders. The first being schematics. This has PDF files of the schematics. Excuse me. And there are two options that I give. One's called a full build that has all the parts. I also list an option for what's called option 1. And what that is for the Monkey Do project, we don't need everything that's on that board. So it's just a schematic that shows things we don't need crossed out. So that's a nice feature of Altium Designer. It can do that for us. But if you look at the full build, that shows everything that's on the schematic for the default full build. So let me close that. The PCB folder has the Gerbers in the Gerbers folder. In there are the raw Gerber files. There's also this list through Oshpark here, or this folder for Oshpark that gives you those versions of the Gerbers. But I also include a PC fab note drawing. All this is is a simple drawing with a reference of a dimensional reference, notes on board construction, and a layer stack up that kind of matches which Gerber files go to what layer. So that's nice to have. Now the last folder is the CCA, or circuit card assembly folder. This has everything else we need to get the board, a board built. So we use the PCB files for the raw PCB, but in here we have everything else. So the first thing you'll notice, there's two BOMs, one for this full build and one for this option 1. I'll just open up option 1. And it's a nice bill of materials that has quantity designator, manufacturer, and also a supplier. And almost everything here you can get from DigiKey. And if any of these happen to be out of stock at the time, well, these are very common components. They were in stock at DigiKey at the time when I generated this BOM. But you have a full bill of materials. In addition to that, I always like to make what are called these assembly prints. What these are nice PDF files that give a top and bottom view to aid whenever you're assembling. It's a blown up version. This allows you to see all the trace routings, everything, without having to open the raw design files or the Gerber files. So there's a top and the bottom. Now, an interesting part about this is you notice there's a full and an option 1. Assembly sheet. And so what happens is that it takes off the components that aren't assembled, so you don't even see the pads here. So that's kind of what the tool does. We also have pick and place files. So if you happen to really want to send it to place, do pick and place. The files are here. So we'll leave it at that. Those are all the files. So let's actually take a quick look at the schematic. Now I'm going to open up the schematic and we're going to look through it in Altium Designer, only because it's a little bit easier for me to zoom around. Let's open up the schematic here. Now I'm just going to step through really quickly some of the highlights here just to point a couple things out. The first, at the top, I have this boxed area called Freedom Header Interface. Now the way this is designed is that I got the pinouts for some of the more popular Freedom boards. And basically what I did is just listed all the net names for each of the various the boards. So notice this is J9 here, but I also said on the KL25Z it's J9. But on the 46Z, it's the J3 or J3 in the K64F. And here's the port signals that are attached. Now, if there's nothing listed under a name, that means it's not connected. And lastly, what I did is that because we have many different names for the same signal, I kind of assigned this generic net name. Like IO0 is the same as PTE31 on KL46, or PT8 on, for example, KL25Z. So that's how it's laid out. Now, when I designed this board, I did it for the KL64F in mind, but I had these other ones here just in case you wanted to remap it. And where it was made sense is that on the outer pins, I also list what the Arduino R3 signal names are and what those map to as well. So it looks like a lot, but that's all that is. It's just a way of naming the pins for these different boards. So I'll slowly step through here. First thing, we have some solder pads if you want to bring external power into the board. There's a section here for the Wi-Fi, the RNXV interface, and it's pretty simple. You notice I have a handful of I/O tied to the header. If you look through the data sheet in the RNXV, you'll make sense why. There's a reset pin. There's a pin to select if you want the ad hoc or defaults for default mode. There's a pin that gives the TCP status. I believe that's GPIO 6 that's used by the WebSockets interface on Mbed. Now what I did, and there's a note here, and you can read through that note, but I'll just explain it, is that the UART, TX and RX, I actually have two different connections that you can possibly do. we go here to what's called TX and RX, these nets. This is kind of like the default connection, and if you wanted these, you populate these 0 ohm resistors. But there's also an alternate connection, and here's the reason why: is that TX and RX go to J19 here, which go to the Arduino R3 TX and RX pins. Now these always map to a serial port on the Freedom boards. The problem is that in some of the Freedom boards, they also map to the virtual COM interface, and it would be really nice to separate those out. So to do that, I provided alternate pins that you could use, RX alt and TX alt. And that's up here. So, for example, on the K64F, there's another physical serial port if you want to use that. Same with the KL25Z and I believe the K20D50. The KL46Z does not have a UART there. You'd have to use software UART if that's what you wanted. But that's how that works. So let me zoom back down here. Oh, I'll scroll over the RS. The RS45 interface is also wired up the same way. You can select the main UART or the alternate. Now, the other thing in the note is on the receive out of these, all of these chips, there's a series 2.2K resistor. That's to keep electrical sanity because we have multiple drivers and they're normally high, so that one person can pull the bus low and it doesn't drive the bus crazy. Now you can't have more than one thing talking at one time, but it at least keeps electrical sanity. I have some optocoupler interface. Notice it's diode protected. I have a diode this way. And this circuit was primarily designed for 120 volt AC input, hence the scaling of this resistor. It's quite large. That's the other reason we have the diode to handle the reverse case, because the LED inside of the Mach D207 cannot handle that reverse potential. And we have a simple open collector output with a 15K pull-up. Now, if you do feed an AC signal into, for example, T1 and T2, R7 is going to toggle at 60 hertz. So you just have to keep that in mind when you program. Now, if you want lower voltage inputs, you'll have to adjust the resistors R8 and R10. We have a semiconductor temperature sensor, very easy to use. In the example code for the Monkey Do, we use that. You can look that up. I have this thermocouple interface over SPI. Now, I don't use this in the demos, but I have pads in case you want to play with it. If you have a thermocouple you want to talk to, they're a little more complex, but this chip takes a lot of the difficulty out of the thermocouple. Now, one thing I'll point out, if you want to use the thermocouple, you cannot use the alternate TX-RX, because they're shared by the SPI pins that go to the thermocouple interface. We have RS45 I talked about. Now, lastly, we have two solid-state relays. One is a high current and one's a low current. Now, these are what are called triac outputs, so they're meant for switching AC signals, like 120 volt AC. So you can look at the data sheets to learn everything you need to know about how these work. They work a lot like an optocoupler. Basically, you forward bias this LED. That light turns the triac on and will allow current to flow through here. So if you hook, for example, your input hot side to J4 and then your load hot to J5, that's all you need, and tie the neutrals together and you got a nice circuit. Now, with both of these, the only real difference is their current handling capability. One is 10 plus amps, and the other one's like an amp. Is that you notice I have two IOs on each one of the inputs. That's because you have to drive these LEDs fairly hard, and these are meant to be driven together. So when you configure these as high current outputs, you have to both configure them as outputs and drive them on together, or it won't work. But it's a pretty that's a pretty common method of increasing drive strength. So that's a quick overview. So take a look if you're interested in building it. Go ahead. If you have any suggestions about future improvements, certainly let me know. Thanks.